It says to look at table 19.7, but it has the answers on there, so I didn't copy that over there. We don't need that ionization equation. We can write a generic one for weak acid. So we can write that as HA as the weak acid, and that's going to dissociate or ionize into a hydrogen ion. That's what bronzite laurate acids do, and the conjugate base. The equilibrium expression for that weak acid is going to be Ka is equal to the product of the concentrations of the hydronium ion and the conjugate base over the concentration of the weak acid. This is all at equilibrium at a specific temperature. Typically, we'll need to set up an icebox for this. In this case, we are given the value that we're exactly looking for, so we don't need to do that. But I'm going to do it anyway just to go through this methodically as all the other problems. We're going to set up initial conditions, the change in concentration, and this is really what we're looking for, the concentrations at equilibrium, because those are the only values we can use in an equilibrium expression. All right, so the initial concentration is given to us as 0.1000 molar. Okay, and sometimes students will put that right into the equilibrium expression. That's not right. This is not an equilibrium concentration, so careful not to do that. Initially, there are no products as they haven't been made yet, and you would set the change to be some quantity positive x. Change of the reactants is going to be used up, so it's negative x, the same amount. And then you would get the equilibrium concentrations to be x and x for each of the products, and your initial concentration minus that change to get your concentration of the weak acid at equilibrium. Okay, so that's just the initial plus the change. In this case, since the change is being used up, it's minus. So we don't need to do any of this, but that's how we would typically approach this kind of problem, because in this problem we are given concentration. We'll just plug that number right into, we don't need this ice box, but we're just going to do it. So this is going to be the same concentration. All right, so the change must have been that amount because it started at 0. And then that change must have been minus 1.34 times 10 to the negative 3. And then the final equilibrium concentration at equilibrium is going to be the initial plus the change. This is what we were going for. Now we can use those to just plug in there. So plug those values in, and you'll get your answer. Ka is equal to 1.34 times 10 to the negative 3. I don't feel like writing that twice, so we'll just square that. And then the concentration of the weak acid at equilibrium is 0.1 minus 1.34 times 10 to the negative 3. 3 significant figures there. We got 4 there, so we're going to keep 3 in our final answer. Punch those numbers in. And we got Ka is equal to 1.82 times 10 to the negative 5.